All right, Newton's second law. Let's start with the old version, right? The version that we've done forever. And that version has been, we've been living in the linear world, right? And so if I have a, let's say, a 5 kilogram cart that is on frictionless ice, right? And I apply a force of, God, all right, we got this. We got this. Never mind. Okay, we got a force applied of, I don't know, let's say 10 newtons to pull my cart across the frictionless ice. Well, I've got a constant force, right? So let's draw the free body diagram. That sounds like a good idea. What do we got going on here? Force of gravity and force normal. And we've got this force applied, right? And I'm on frictionless ice, and my cart is not plummeting through the ice, nor is it being ejected off of the ice. So I can pretty safely say the normal force is equal and opposite to the gravitational force. And there is the net force in, the net force in the y direction is 0. But in this horizontal plane, I have a net force because I don't have any friction, right? That's this applied force. So if there's a net force, gang, there's an acceleration. And we know that we can find that acceleration because of the beauty of Newton's second law, right? Which tells me that the acceleration of an object is equal to the net force that's acting on that object divided by the object's mass. So the bigger the mass for a constant force, the smaller the acceleration, right? The bigger the force for a constant mass, the bigger the acceleration. So if I plug in our stuff here, we're going to get that the acceleration is equal to the net force, 10 newtons, and the mass, 5 kilograms. That's pretty easy math, gang. The acceleration equals 2 meters per second squared. Bingo. All right, that's old news.
What's up, my mama's class?
All right, now the new news. Okay. That is, we're not living in the rotational world anymore. I'm sorry, the linear world. We're living in the rotational world. And the good news about our rotational world is everything's the same. Newton's laws still apply, right? But it's just slightly different. And that's the thing that is sometimes confusing. But don't let it be, all right? It's okay. So in linear world, we say force causes acceleration. Right? In the world of rotation, torque causes, can't spell, rotational acceleration. Okay? In the linear world, we know that mass is the same thing as the inertia, and it's that resistance to change in motion. In the rotational world, it's not just the mass, right? It's the mass and where the mass is located. So we have this equation of the generic form, right? ml squared. And depending on the shape of the object, there might be a fraction in there, okay? But there might not. All right, so we still have something that causes rotation, it's just torque. We still have something that resists a change in motion, right? It's the rotational inertia. So as you might imagine, if I've got a force and a torque that causes rotation, and I've got, maybe I should write out that torque is, right, the force times the lever arm times the sine of theta. I've got a torque that causes rotation. I've got a rotational inertia that resists that change. So I've got Newton's second law of rotation, which says that the acceleration, we'll talk about that alpha symbol here in a minute, is equal to, it's the net torque divided by the rotational inertia. Now see, it's the same idea, right? The symbols aren't the same, and the equation isn't identical, but it's certainly a mirror. What causes rotation? Torque, right? What's rotating? An object. How do I describe that object's inertia? Well, how much mass is there and how far away that thing is from the center of from the point of rotation. Now, what's going to happen in our next module, we're going to talk about kinematics in this rotational world. And here's one of the big things, right? What happens in the linear world is pretty darn similar to what we're now going to learn happens in the rotational world. Those same kinematics equations that we used in September, we're going to be able to use here in rotation in February and March. The difference is, and how we can tell the variables apart, is that instead of using A and V and X for distance, we're going to use Greek letters, right? We're going to use alpha. And there's going to be a new symbol for velocity. Okay? And there's going to be a new symbol for the distance. And it's okay, because it's the same idea, gang. Guess what? Rotational acceleration is still the rate of change of the rotational velocity. It's still the same thing. Our variables just look a little bit differently, right? So for now, here's what we need to know, right? When we talk about the kinematics in module 6.2, we're going to dig into like how to apply this and how to use it. For right now, what we need to know is, hey, if I want to accelerate an object in the rotational world, I apply a torque to its mass, right? And so this is Newton's second law. Of rotation. Okay, there you have it, gang.